Hello, and welcome to Speculative Automated Refactoring of Imperative Deep Learning Programs to Graph Execution. My name is Rafi Kachadorian, along with my co-authors Tatiana Castro-Velez, Meni Bangarazadeh, Nanjia, and Anita Ranja. This is a presentation that will be held at the International Conference on Automated Software Engineering in November 18th, 2025 in Seoul, Korea. So deep learning systems and runtime performance are important. So as machine learning, including deep learning, gets increasingly pervasive, efficiency becomes essential to support ever-growing data sets. Traditionally, deep learning frameworks have embraced what's called deferred execution style programming that supports graph-based deep learning neural network computations. However, it has been shown to be error-prone, cumbersome, and produces programs that are difficult to debug. Because graph computation executes statements in a non-imperative order, furthermore, traditional software engineering tools cannot assist with troubleshooting deep learning programs written in this style, for example, debugging tools, very easily. Here is an example of a deep learning program written in the deferred execution style. Here we can see that lines 2 to 4 build a computation graph. Lines 4 does not execute actually until a session is run on line 10. And in this model, there is no native support for common iterative imperative programming constructs, for example, iteration. So along comes imperative deep learning programming, led by deep learning frameworks such as TensorFlow, Eager, Keras, and PyTorch. And these frameworks encourage an idiom that's called eager execution, which is sort of like your more natural, less error-prone, and easier to debug kind of coding. However, it does sacrifice runtime performance. Thus, hybrid approaches, and some examples are MXNet Hybridize, TorchScript, and Autograph, which is part of TensorFlow, have come about to sort of bridge the worlds together. And what these approaches do is that they execute the imperative deep learning programs as static graphs at runtime and have been since integrated into mainstream deep learning frameworks. Here is an example of an eager TensorFlow of imperative deep learning model code. It is written in the Keras idiom as well. So here we're going to add what's called TF function decorator on the call method of the model. And we do that to potentially enhance performance. At runtime, this method's execution will be traced. This particular example, we'll actually see a 9.22 speedup. However, hybridization does have some drawbacks. So one, it does need quite a bit of metadata, so you need to specify which methods and functions need the decorator, the ones that are going to be hybridized, or what's called traced at runtime. There could also be some metadata involved there. You need to be cognizant of what kind of programming constructs you're using, what you're doing in these methods as far as what the code is doing. There are subtle considerations for specifying or decorating the functions to be migrated in such a way that the code is safe, accurate, and efficient at runtime, and also to avoid performance bottlenecks and semantically equivalent results. So this requires a lot of manual analysis and refactoring in order to be optimal and could be error and omission prone. And it's furthermore complicated by the increasing amount of object orientation and found in deep learning frameworks and idioms, as well as, of course, dynamic type languages such as Python. So just to show you an example of where hybridization can go wrong, here we have a function f decorated with TF function. And it actually has a side effect producing line on line 3, which is actually printing here to the global standard out stream. But in general, side effects can be problematic for hybridized functions and methods. Again, this printing listing, depending, for example, global variable mutation. And the reason is that because they're traced at runtime, the function behavior is really etched into this corresponding graphs. What happens is that the side effects either occur on the first execution of the method or not at all, because they're basically captured as part of the execution graph. So this can result in unexpected results, executing the side effects multiple times, or as I said, not at all. Side effects occur when the TF function is basically a call for the first time, and subsequent calls with similar arguments as far as their shapes and data types are executing the graph instead. So our insight into this problem is that although imperative deep learning code executes sequentially, hybridization does resemble some parts of parallelizing sequential code. So for example, in parallelizing sequential code, one must also avoid things like side effects for concurrent programs. And our idea for this problem is to adopt some of the concepts from automated refactorings that parallelize sequential code into this domain. So we introduced two new fully automated refactorings, one called convert eager function to hybrid. So this one is going to transform your otherwise eagerly executed imperative. This one works in Python. Deep learning code for enhanced runtime performance. This will automatically decorate appropriate functions to execute as graphs at runtime, and it will avoid or try to avoid hybridizing code under certain conditions. For example, side effect in code in order to preserve semantics. The other one is called optimize hybrid function, and this actually works on code that's already running as graphs and tries to optimize them for optimal runtime performance. This one actually could possibly dehybridize code when eager execution could be faster. There's a phenomenon called graph retracing that will create runtime graphs too often in such a way that you were actually better off with not hybridizing it in the first place. It also issues some refactoring warnings when the hybrid code may have unexpected results, but the refactoring is not possible due to semantics preservation. So we're not going to dehybridize those kinds of functions that may have actually unexpected results, because that is a change to semantics. Here are some example preconditions of these two functions, and the implementation basically goes through the code to check which of these conditions are met, and it applies the appropriate refactorings. Here is a high-level flowchart of how the approach works. The approach does consist of a novel whole program static analysis for an imperative deep learning program based on the WALA Ariadne analysis framework. It is currently working with TensorFlow, but it is extensible to other deep learning frameworks such as PyTorch. We introduced a novel Python side effect analysis based on the WALA modref analysis for Python, and it leverages a complementary speculative analysis to resolve complex cases, and it basically does that using like contextual deep learning keywords like train and other kinds of deep learning frameworks that it would expect to see in like method names and variables, etc. Here's a screenshot of our implementation that is actually written as a PyDev plugin for PyDev Eclipse that uses the Eclipse refactoring framework for Python and ties in WALA and Ariadne together. Some example evaluation statistics that we have here. We have analyzed 19 open source Python imperative deep learning systems of varying size and domain, and they range from 0.12 to 36.72 thousand source lines of code. And we found that we were able to refactor about half of these functions, 766 candidate functions in all, despite our very conservative approach, especially since we're dealing with not only an object-oriented language, but also a dynamic one. And some statistics on the runtime performance evaluation that we measured an average relative model training speed up of 2.16. Again, this is fully automated. We have not yet measured the memory consumption, but I would expect that it would actually use more memory, but you're basically sacrificing the memory for speed. And we also took a look at the differences in model accuracy and model loss before and after refactoring. We found that these were negligible. So that gives us some confidence that the semantics are being preserved, despite refactoring of a dynamic language. So in conclusion, imperative deep learning code is easier to debug, write, and maintain. However, it comes at the expense of runtime performance, and hybridization techniques have bridged the gap between eager and graph execution. However, using hybridization efficiently and safely is not very easy to do. So we introduce automation to assist developers with this task. And our refactoring approach automatically converts imperative deep learning code to graphs. It features a novel tensor analysis for imperative DL. And we use our open source tool that successfully refactored about half of the candidate functions across 19 Python deep learning programs and systems, resulting in an average relative speedup of 2.16. And for more information, please come see our poster. Thank you very much.